practice now. I leave the theory, but I'm going to be obviously informed by the theory. I'm going to start with the data collection. There's the data collected in many systems. You can think about your subsystem and so on. In an emergency department, for example, you have data on the timestamps of when people arrive to the system and so on. I'm going to create an event log out of this, which is essentially the same tool that Zheng Heng said and explained, and I explained when we talk about what type of data we have. Obviously, questions of unavailable data, I'll show you how we deal with them a little bit, but we can create essentially an event log which tell me, hey, job number, timestamp, what happened in this timestamp, what activity happened in this timestamp. So this is, when I take this event log into process map tools, I can create essentially a network, a queuing network that is the network that created this data. And I can create some dashboard that I can show you different performance of your system. The blue one is the dashboard. The trick is, and this is where the power of SiMLQ comes to play, is that I can use machine learning to also now create a simulation model of this queuing network. So after I learned this process, rather than using structural causal queuing models, I'm using process mining and queue mining to do this, because this is a theory we just started developing. But I can get this, and I can now run a simulation model. All of this takes seconds to do. I'm going to show you that it takes seconds. Don't just take my word for it. Then I can do what-if analysis. Once I know the current system, and I know how to create copies of the current system well, and I know, oh, what happens now if I speed up one machine? What happens if I add a doctor, I take a nurse off the field? What happens if diagnostic service becomes faster, slower? Do what-if analysis, do the action selection, how much it costs me, what is the benefit, which those who do optimization can see how I do this. I'm going to run the simulation along interesting interventions, and I'm going to know their cost and find out what is the best one. I'm going to take an action. I'm not a guy who takes action in practice, right? This is for the business to take action, to choose what action they want to do. This is the manager work, the change of management. And the trick is that once I change this action, I am changing the data, right? I'm moving to a new system. That's why it is so important for me that SiMLQ can take me from 1 to 4 in seconds. This is the difference between a simulation model that would support this to a digital twin that will support this. I immediately get an updated simulation model of the current system and not the older one. And now I want to change the updated system, and I can continue this loop. Does this make sense, guys? Are you as excited as I am about it? Good. Okay, so these are the guys who work. I introduced Dimitri and Arik already. Amir, Parvin, Shani, Ali, and Vlad are development and R&D team. I'm going to show you how SiMLQ works. That's what I hope to be able to do. So feel free to raise your hand if you have questions. I can stop it in the middle, and let's have some fun. 5 minutes of a video, and I can shut up for a little bit.
Of SiMLQ. First of all, before we load
you hear it well enough?
Let's take a look how an event log looks like in the wild. An event log is a data set that contains a case ID, this is an identifier of a patient, activity, which is what the patient was doing in the emergency department, for instance, and a timestamp that shows when the event of triage, registration, assessment happened. In addition, there could be multiple attributes like initial zone, age, gender, and triage description that help the machine learning engine of SiMLQ to better learn and fit a digital twin. Going back to SiMLQ, we will load the data sets, annotate where the case ID is, where the activity column is, where the arrival time is, and the additional attributes like age and gender.
So I'm stopping it here for a second. 3 notes. One of them, this is real data from an emergency department in Toronto. It's cleaned, it's simplified to make it nicer visually, but it's real data. You see things in real time here. And what also you see, going back to the question about data, is that I don't really have all the data I want. As a queuing theorist, I want to know when you arrived and when you started service and when you finished service, right? I don't have this. I only have one timestamp here, only the arrival time for different activities. So what we're going to do is, if we have two stations here, I will take the arrival time to Amir as the end time of my station, right? That's an easy trick. But I don't know the waiting. I don't know to differentiate between service and waiting. So it's a tough problem for us as queuing theorists working with data. And that's why I think, like me, you'll be impressed from the accuracy that you see in the simulation results that I'll show you soon. Questions so far?
Yeah, I'm a bit thinking purely with respect to emergency department, right? I would have thought that timestamp would have recorded all of this information as being able to track what an individual customer performance was. You know, like somebody arrives.
So no, that was what was my thought as well, and ends up as not being true in the vast majority of places. Neither one of the emergency department in Ontario that we work with has this data. In general, the IT systems of organization capture well financial data. They need to know that Dr. Amir has seen me, so they can charge OHIP for a doctor seeing me. They don't care about how much time it took him. That's not their financial problem, so they don't record it. Luckily, because they pay him possibly by the hour, I know his shifts. Otherwise, even this wouldn't be there. But yeah, we are living in a world where the beautiful data that Zhengheng and I use, kind of in the structural causal modeling, doesn't often exist in practice. It does exist in several places. So there are hospitals, walk-in clinics that we know that have better data sets using RFID and so on. But that's a great point.
And once the data is loaded into SiMLQ, we will essentially receive a process map of the flow of patients. This is an emergency department data where patients start, go through triage.
So we learned it in 2 seconds, as you've seen.
Then 322 out of the 2,752 patients go to consult request, consult arrival, and then all patients are disposed. The rest of the patients follow this direct line from assessment to disposition. Disposition is a decision whether the patient is admitted or released home. We can also look at various statistical dashboards, look at the arrival process, look at the number of patients in the system, the length of stay, including the average length of stay, the 90th percentile, and so on. On the right-hand side, we have the start date time and the end date time, which is the time frame of the dataset.
Okay, so a quick notice up to here. This is all descriptive analytics, right? The blue is the data. That's what you've seen in the data. You see Sunday, Monday, Tuesday, Wednesday, 2 weeks essentially of arrival with the variations of that performance measure. Those are true from the data. I can define some other performance measures. This is descriptive analytics. Nice, sophisticated descriptive analytics.
We can also add new metrics. Let's add the PIA metric, which is the physician's initial assessment. It's a very important metric. It's a length of stay metric that connects registration or triage, the latest, to the assessment process. We add the metric, and now we're able to see that this is a user-defined metric called PIA. The average is 3.22 hours, the 90th percentile is almost 6 hours, and we also get a histogram of the PIA. Going back to the map, we can now start intervening and improving our process. So what we're going to
do is where we start comparative analytics, right?
Analyzer in SiMLQ, which is a unique feature that allows the decision maker to perform changes at the activity level. Going to the longest activity that has an average of 2.4 hours and the 90th percentile of 5 hours, which is the assessment. What we're going to do is apply a simple intervention. We're going to speed this activity up by 50%, save the intervention, and now what we're going to do is we're going to simulate a digital twin, which is a machine learning model that learns the system and applies the intervention. Going back to the dashboards, we will be able to compare the original system, which is depicted here in blue, to 2 systems. One is a baseline simulation system, which is the digital twin without any interventions. The other is an intervened model simulation, which means that basically the speed up intervention that we applied in the assessment station is going to be presented and its impact is going to be analyzed using these dashboards. Now that the simulation has completed successfully, we're going to enable the baseline simulation model, which is the digital twin. And we see a remarkable match on all parameters. The length of stay is matching, the number in the system, and so on. So the yellow here means the digital twin representation of the system, and the blue is the original data. It's not a 100% fitting model, but we only use 2,700 cases. If we trust our digital twin, we can remove the original data and add the intervene model that shows what happens after we speed up. We see the impact. The average number of patients in the system reduces to 27 instead of 36. The length of stay reduces by more than an hour. And the PIA, Physician's Initial Assessment, an important measure in emergency departments everywhere in the world, basically, reduces by more than an hour from 3.3 hours to 2.16, with a remarkable reduction of the 90th percentile from 6 hours to 3.8 hours. And we can drill down and explore it further using the different histograms. And this is the magic of SiMLQ. We were able to ingest the data on the fly, build a digital twin, intervene on the digital twin, and assess the impact of our intervention. Thank you for your attention.
All right, so I hope you enjoyed seeing this loop basically crushed from 1 to 4, essentially, and to 5 very quickly. Yeah.
When you make those changes, people will also change how they behave.
Yes.
So that the simulation you have is under the change, assuming everybody behaves the same.
Yes.
So now when you have that feedback loop,
Exactly.
you have to wait long enough to get enough
Yes.
data to see that.
Yeah.
Okay.
Yeah, for sure. Now, if I know how people's behavior changes, because I understand strategic arrivals, for example, I can include this in my simulation model, but that's not in here. Now I'm kind of taking it from, the idea is to some extent to democratize a queuing theory, right? Why we started the work with Zhang Han? I want to say, hey, I'm a queuing theorist, I'm really good at it. Let's see what a data scientist can do. Probably I can do better, but they do something easier. The trick is that we have many people who are trained as data scientists today. We don't have many people still trained as queuing theorists, right? So that's the idea. And then I will need to observe enough data, right? Yeah. Guys, I'm past my time, so I want to finish quickly. Remind you what we've done, talk a little bit about management analytics and how, just a model to how to think about it. Then I showed you a couple of places where we use machine learning models to solve simple queues. Their motivation there was it allows us to do comparative analytics much quicker than in our standard fashion, which support prescriptive analytics, which is all what we want to be able to do, give you some recommendations of what is a better decision to take. We then talk about causal queuing models, and Zheng Han kind of took us through his journey of how he goes from data to comparative analytics, performance evaluations, without knowing many of the things that we need to know when we come to analyze queuing systems. And I show you how SiMLQ takes essentially the same train of thought, but with somewhat different things. So rather than kind of using structural causal queuing models, what we use is process mining to find the real system, right? And we then went with this very similar train of thought of, oh, now I need to simulate the system. I need predictions of what's going on in each one of these stations. I need the routing, I need the priorities, all of these wonderful things that we as queuing theorists can think of. We combine them together, we can run them behind the scene and show you the end results. Critical is the comparative analytics capabilities, right? So I don't know of any better way of doing these things today. There's a special issue of Service Science that I'm editing. With Dash and Arik. Please submit great work there. And thank you. Thank you, Jahan. I don't know if we have time for questions. I'm kind of, yeah.